Hello everyone, I am Bong Jingren and this is my buddy.
Dae
So today we will discuss about the analog electronic lab 2, which is the operational amplifier using LT-SPI. So in this experiment, we will investigate the characteristic of the LM741 operational amplifier. There are three main objectives we carry out this experiment. So the first one is to understand the basic characteristic of operational amplifiers circuit or configuration. The second one is to compare the theoretical and the experimental duration values in each configuration. The last one is to determine the effect of capacitor, bypass resistor, and internal operational amplifier offset voltage to the output voltage. So I am covering the first two experiments, which are inverting and non-inverting amplifier, while my buddy will cover the rest three experiments, which are summing, differentiator, and integrator amplifier. Okay, so now I will show you our experiment A result. Okay, so for the inverting amplifier, we set R1 to 1k ohm and R2 to 33k ohm, giving a theoretical gain of negative 33 according to the derivation gain AB equals to negative R2 over R1. However, let's look at the simulation result. The output did not reach 33 volt. Why? As you can see in the graph, the waveform was split at approximately 14 volt. This happened because of the saturation voltage constraint. The LM741 was supplied with 15 volt, and op-amp cannot output more voltage than its supply with. As according to the datasheet, the output swing is typically 14 volt. So for the inverting amplifier, we set R1 to 1k ohm and R2 to 33k ohm, giving a theoretical gain of negative 33 according to the derivation gain AV equals to negative R2 over R1. Alright, now I will show you our experiment B. In experiment B, we set the R2 become 10k ohm instead of 33k ohm in previously. This is because we want to obtain the output voltage with lower value, so the output voltage will not be big. In contrast, the non-inverting amplifier had a gain of 11 according to the derivation gain AV equals to 1 plus R2 over R1. Since 11 volt is within the saturation limit, so the sine wave remain perfect without flip.
Okay, now in the experiment 3, we're doing the integrator. Now in the integrator circuit, we set the input in the 1 watt square wave and we get the output of a triangular wave. This shows that we have successfully converted a square wave into a triangular wave by the integrator circuit. However, there is an important addition of the 10 mega ohms feedback resistor in the circuit. In ideally situation, we don't need resistor, but in the practically, the real op-amps like the LM741 has a small input bias current. If without this resistor to provide a DC feedback path, the capacitor will charge up from this error current and saturate the op-amp. In the pre-lab calculation, we get the 1 kilo values, and after compared with the experiment, we also get an approximate negative 1 kilo value. This shows that we have satisfied the integrated op-amp circuit. In the experiment D, which is the differentiator circuit. Now, in the differentiator circuit, we set a triangular input waveform and we get a output waveform which is approximately to the square wave, but there has a small oscillation noise at there. Similarly to the integrated circuit, for the differentiator circuit, we have add a 100 picofarad capacitor in parallel. This is to stability the output waveform. A pure differentiator amplifies the high frequency noise. The small capacitor limits the high frequency gain to prevent the oscillation. That's why we get a small oscillation at the output waveform. Now let's look at the calculation part. We have successfully convert the triangular wave to the square waveform. In the calculation part, you can see the previous calculation. We get a negative 2 watt, and the experiment voltage result is also the negative 2 watt. In the experiment E is a summing amplifier. The summing amplifier is a vector additional circuit. We 1 watt, totally 1 watt input on both channel. The channel 1, which has a resistor with resistance 1 ohms, and the channel 2 is the resistor with 2 kilo ohms resistance. In the channel 1, in the summing amplifier, we will sum up the two output and get a total output is 6 watt. This can show that from the waveform graph that we get a inverted waveform with 6 watt in the finally output. Now the result was 6 watt, which is match our calculation perfectly.
Okay, now I will continue the conclusion part. So in conclusion, our lab objective were achieved, which is the 5 LM741 op-amp circuit were tested and verified. So the LM741 behave according to ideal formula only within specific limit. We learned that the power supply range limit the maximum gain, which is the clipping value, and non-ideal characteristic like bias current require us to add extra component like bias resistor and stability capacitor for stability in integrator and in differentiator. These trade-offs are essential when designing real-world analog circuits. That's all for today. Thank you.